Has anybody ever told you that you have potential? Today we're going to find out what they meant by that. Good morning, good afternoon, or good evening, ladies and gentlemen, and welcome to lesson 8.3, which is all about electric potential. If you need to go back and review lessons 8.1 and 8.2, now would be a great time to do that because we will be using some of the concepts from those lessons in this lesson. Now, first of all, let's review potential energy. As you may remember from a previous chapter, potential energy is the energy of position. Now, when we talked about potential energy previously, we refer to potential energy in terms of gravitational potential energy. So in other words, if an object rises in a gravitational field, then it gains potential energy. And if it sinks or falls in a gravitational field, then it loses potential energy. It takes work to cause an object to rise within a gravitational field, and the amount of work that you do is equal to the object's change in potential energy plus its change in kinetic energy. Remember, kinetic energy is energy associated with movement and velocity. Now, if the object is rising at a constant velocity, then the amount of work is simply equal to the change in potential energy, which is equal to mass times gravity times the change in height. We are assuming that the gravitational field remains constant, which means that the object is rising a relatively short distance, and so the Earth's gravitational pull is not decreasing noticeably over that short distance. Just as it takes work to move an object in a gravitational field, it also takes work to move a charge against an electric force in an electric field. If we move a charge in a direction that is opposite the direction of electric force, then that will cause the charge's potential energy to increase. So for example, imagine we have two positive charges. Now we know that like charges repel each other. So if this charge is fixed in place, then this charge will feel a force pushing away from the other positive charge. If we wish to push the two charges together, that will cause the potential energy of the situation to increase because we are pushing this charge in a direction opposite the way that it really wants to go. The same is true if we have two negative charges. Just as two positive charges repel each other, two negative charges also repel. So if we try to push these charges together, the potential energy consequently increases, and it decreases as we allow them to move further apart. Now, when two charges attract each other, it's the opposite situation. These two charges want to pull closer together, so it actually takes work to push them further apart. We increase the potential energy of this charge if we push it further apart from the positive charge. Now remember that gravitational potential energy is equal to mass times gravity times height. So if we want an electric analog, we replace the mass with charge, we replace the gravitational field with the electrical field, and we replace the height with the distance between the two charges. This is the formula for electric potential energy. Now you'll recall from a previous lesson, I hope, that the electric field strength is equal to K, the electric constant, multiplied by the strength of the charge that is causing the electric field, divided by the radius, or the distance squared. I keep wanting to say radius for R, but in this case R just means distance. And so we can take that value, or that formula, and we can plug it into QER. We can say the electric potential energy is equal to Q times K times big Q divided by R squared times R. And what will happen is that one of those R's will cancel out, and so we can say the electric potential energy is equal to K times big Q times little q divided by R. So please note that when we calculate electric potential energy, R is not squared. Because R is not squared, it drops off inversely with distance, whereas electric force drops off inversely with the square of distance. Again, please go back to lesson 8.1 if you need a refresher on Coulomb's law. So imagine you have two charges which will represent as big Q and little q, and they are separated by some distance R. And when they are separated by the distance r, then the electric force between them is Fe, and the electric potential energy is Ue. Now, if we double the distance, if we move these two charges so they are now 2r distance apart, the electric potential energy will only become half of its original value. If you double the distance, then the electric potential energy decreases by 1/2. However, the force between them will decrease to 1/4 of its original value because electric force is inversely proportional to the square of the distance. Likewise, if we triple the distance between the two charges, so they are now 3r distance apart, the electric potential energy becomes UE over 3, but the electric force decreases to Fe over 9. Just to hammer that point home, here's a chart, or here are two charts rather, showing the changes in electric force and electric potential energy as two charges get further and further apart. And although the charts superficially look similar, you can see that the electric force drops off much more quickly because it is an inverse square relationship, whereas the electric potential energy drops off more slowly because it is simply an inverse relationship, not an inverse square relationship. So that brings us to our first skill practice question. It says, how much work is required to push two positive 20 microcoulomb charges together from a distance of 5 meters to a distance of 1 meter? All right, well, as we were saying a minute ago, the amount of work required to push these two charges together will be equal to the change in electrical potential energy, which is equal to the difference between the electric potential energy when the charges are 1 meter apart minus the electric potential energy when they are 5 meters apart. So I'll call that U1 minus U5. When the charges are 1 meter apart, they will have a greater electrical potential energy because they're both positive. They don't want to be close together. So putting them close together will increase their potential energy. Putting them far apart will decrease their potential energy. So we'll have U1 minus U5. All right, now, to replace U1 and U5 with formulas, we can say K times big Q times little q over R1, where R1 is going to be 1 meter, minus K times big Q times little q over R5. And because K, big Q, and little q are not going to change, I can just factor those out. So I can have K times big Q times little q multiplied by 1 over R1 minus 1 over R5. I have to keep the R1 and the R5 in the denominator, okay? We can't just flip them up to the numerator simply because we factored out K times big Q times little q. So this is the simplest formula we can possibly get. We're going to have to plug in some numbers to solve for work. And you know what? I don't really feel like writing out all the numbers, so I think I'm just going to snap my fingers and make them magically appear. Here goes. There, that's much better. Before we go any further, take a look over all of this. Make sure you understand where each of these numbers came from. I had big Q times little q, but because they're both the same, I just squared that number. Remember, that's a shortcut you can take when both charges have the same magnitude and sign. All right, next, I'm going to go ahead and square this number. And then for this thing here, I'm subtracting two fractions that have different denominators. I need to get a common denominator. And 1 and 5 will both go into 5, so I'm going to change this 1 over 1 to 5 over 5. And again, I think I'll just snap my fingers to speed up the process. There we go. That sure does speed things up. Also, when I snapped my finger, I magically corrected a mistake I had made in the previous one where I had put this 2 down here when it should be up here. It should be Coulomb squared. So I just went ahead and fixed that all with one magical snap of the fingers. All right, we're almost there. Let me snap one more time. And there you go, folks. When we multiply the electric constant by the product of the two charges, we get 3.6 newtons times meters squared. We take 5 over 5 meters minus 1 over 5 meters, we get 4 over 5 meters. And then when we multiply those together, we get 2.9 joules as our final answer. And that is the amount of work that it is going to take to push these two like charges together. And it does require work because they don't want to go together. This brings us to our next skill practice question, which is similar to the one we just answered, except this time they are opposite charges, so we will be doing work by pushing them apart instead of pushing them together. The question reads, how much work is required to separate a positive 100 microcoulomb charge and a negative 250 microcoulomb charge from a distance of 25 centimeters to a distance of 75 centimeters? We are taking two charges that are opposite. They want to pull together, but we are forcing them apart. So this will require us to do work. And the amount of work that we'll have to do is equal to the change in electrical potential energy, which is equal to the potential energy when the charges are 75 centimeters apart, so I'll call that U75, minus the potential energy when they are 25 centimeters apart. And replacing U75 and U25 with the formulas, that's K times big Q times little q over R75, which is going to be 75 centimeters or 0.75 meters, minus K times big Q times little q over R25. And we can factor out K times big Q times little q, which gives us K times big Q times little q times 1 over R75 minus 1 over R25. Now, once again, folks, I will snap my fingers and magically fill in all of these numbers so that we don't have to wait for me to write in all of those in a slow fashion. Very nice. As before, pause the video, take a minute to make sure you understand where each of these numbers came from. I just substituted in the electric constant, the values of big Q and little q, and the distances that they're starting at, and the distance that they want to end at. Or excuse me, I said that backwards. The distance that they're ending at minus the distance that they're starting at. I'm going to snap my fingers again. We will go ahead and advance this calculation by multiplying these two charges together and then getting a common denominator for these two fractions. Here goes. Okay, so we have multiplied these two charges together to get negative 2.50 times 10 to the minus 8th coulomb squared, and 0.750 and 0.250 will both go into 0.750, so I use that as a common denominator. I had to multiply this side by 3 over 3 in order to make the denominator 0.750. One more step to go. We are going to multiply these two numbers together and subtract these to get our final fraction, and then we will multiply that final fraction by the product here to give us our final answer. And there you go, folks. We multiplied K times the product of the charges, we get negative 225 newtons times meters squared. It's negative because we had to multiply a positive times a negative charge. When we subtract 1 over 0.750 minus 3 over 0.750, we get negative 2 over 0.750. When we multiply those two numbers together, we get a positive value for work, which is exactly what we should get because, as we said before, we will have to do work in order to separate two charges that are attracted to each other. Sometimes it's useful to speak of the electric potential surrounding a charge, but we don't want to have to worry about the magnitude of some other charge that is experiencing that field. And so for that, we have the electric potential, whose symbol is a capital V, and you will understand why in just a moment. This is one of the things that, unlike other symbols that don't match their quantities, this is going to make sense in just a moment. So the formula for electric potential is similar to the formula for electric potential energy, except we do not worry about the second charge. It's just K times Q over R. And instead of being measured in joules, electric potential is measured in joules per coulomb, which we also call a volt. So that V could stand for voltage. Electric potential is just another way of saying voltage, which is a term that you are most likely familiar with. So electric potential is measured in joules per coulomb or volts. For our final pair of skill practice question, we will calculate the electric potential 4.0 meters from a positive 10 millicoulomb charge, and then we will do the same for a 0.2 meters away from a negative 15 millicoulomb charge. Both of these are going to be simple plug and chug type exercises. We have the formula. We'll plug in the numbers and crank out an answer. So for the first one, the electric potential V is equal to K times Q over R. It's not R squared, it's just R. And I'll go ahead and snap my fingers and magically plug in the numbers. And here we are. The value of K, as always, is 8.99 times 10 to the ninth. Plugged in 10 millicoulombs. Milli means times 10 to the minus third, and we divided by the distance of 4 meters. Punch that into your trusty calculator, and you find that the potential is 2.2 times 10 to the 6 volts. Or if you're feeling fancy and you realize that 10 to the 6 is mega, you could also put positive 2.2 megavolts, which just sounds really cool. Now let's take a look at our second problem. We'll be using the same formula. V is equal to K times Q over R. And let's magically plug in those numbers. And presto, the electric potential at this distance will be negative 6.7 times 10 to the 7th volts. And it is negative because this is a negative charge. Negative charges are surrounded by negative voltage. Positive charges are surrounded by positive voltage. I'll leave you with this table to consider, which contains all of the major formulas that we have discussed in this unit. So I would encourage you to pause the video, take a moment to study this table, and make sure you understand the relationship between these four equations. That's going to be it for lesson 8.3. I just realized that I have had the wrong lesson title up here, so that's super helpful. Good for me. Great. But anyway, yes, this is lesson 8.3, electric potential, not lesson 8.2, charging objects. And of course I realized it when I'm done doing the recording. Fantastic. Anyway, I hope you're doing well. Please hop on over to Google Classroom, where there will be a short assignment to check your understanding on the concepts that we have just learned. And join us tomorrow. We will be moving into Unit 9, which is all about electric current and electric circuits. I look forward to seeing you then. Stay safe. Keep washing your hands. We'll talk to you tomorrow. Bye.